Gang, the last video was rather subtle. This one's going to be more advanced. So if you're in a mood where you're like kind of hoping for something kind of cool here, don't have to do much. This video is not for you. This is going to be pretty involved. So you'll need to get R. You'll need to re-examine some old stuff from matrix operations and so on and so forth. So the good news is if you're not in the mood to really get too crazy, you can watch the first half of the video, which is, or actually not the first half, probably about the first 10%, which is pretty tame. So I'm assuming that you've watched the previous video, so I'm assuming that you're an expert on residual plots. Really, there's not much to them. So, but nevertheless, I hope you realize how residuals can be helpful in studying departures from our regression model. And of course, remember our regression model with a one predictor model. Looks like this. Okay. Now, want to get a little bit more specific this time, and let me get this thing out there where you can see it. And I want to look at in this video, I want to look at linearity, and then I also want to show you how to examine outliers. For example, if we have outlier residuals, what do we do? So we're going to look at outliers, and in this video we're going to look at outliers with reference to the y variable, and in the next video we're going to look at outliers with respect to the x. But for right now, what I want to do is I want to just focus on the linearity, and and we'll look at the outlier approach in just a second. Now, the linearity part actually turns out to be pretty straightforward. What we'd like to do is if we have a simple linear regression model, for the most part, we're going to look at one or two plots to examine linearity. The first thing we'd want to do is just look at a straightforward scatter plot between x and y, and if our points appear to be linear, then we can assume that we have linearity, right? Well, not exactly. This is a good way to start, but when I see this, what I have to think is, I'm kind of performing an eyeball test here, and sometimes eyeball tests can lead us to good things, and sometimes eyeball tests can lead us to bad things. So let me give you an example of that. I've got a rather harmless data set that I'd like for you to take a look at. And this data set is just simple x and y, all right? And we have 80, 220, 140, 120, 180, 100, 200, and 160. And our y values are 0.6, 6.7, 5.3, 4.0, 6.55, 2.15, 6.6. I could have chosen a smaller data set because this is getting boring, all right, but 5.75. Now, let me show you the way that a straightforward scatter plot examination via your eyeball test can get you into a little bit of problems. So let's come over to R, and we don't have an Excel and saved in CSV, so we can just enter our data using what I call the C function. So I have 80, 220, 140, 120, 180. Hopefully you can type while I'm speaking. That's why I'm speaking is like this. And our y value were 0.6, 6.7, 5.3, 4, 6.55, 2.15, 6.6, and 5.75. All right? So if we do a plot of x comma y, what we're going to see there is, well, actually, when I did this on Excel, it didn't show that much of a curve. But, you know, it seems maybe reasonable that you could fit that with a straight line. Actually, with this plot, it doesn't even seem reasonable. Okay, so let's fit a model. I forget how to do this always, but if we fit the model of y, well, let's save it as something. We can look at our coefficients, obviously. But I can do plot x comma y, and I can do abline of my model. And I think this gives me my, the regression model on the scatter plot. So guys, you can see that it kind of goes down through the central focus of our data, but and you know, somebody gets sloppy there and does an eyeball test, they could assume that they have linearity. Well, here's a case where it's generally helpful to include some sort of residual plot. So if I take my residuals and save them as residual, all right? Imagine that. And all right. And look at our residual and imagine that we've got a straight line through here at 0. You can see that we have the classic U-shaped. And a U-shaped of our residuals over our x. Now let me point something out here. In the simple linear regression, let's just call these fit. In a simple linear regression cases we're dealing with right here, the plot of our fitted our residuals over our fitted are going to look exactly like that it would if we had fit this as the residuals over our x. Now that doesn't stand true when we get into the multivariate world, which we're ultimately kind of preparing for anyway. So guys, you know, you might get sloppy, I don't know, and not that we ever do that, right? And do a plot there and say, you know, it kind of looks linear, but the residual plot over our original x tends to keep us honest. So a conclusion, residual plots have the advantage. I actually have a couple of advantages now that I think about it. Residuals can be used to examine the linearity assumption, and the greatest advantage, I guess, is that they can be used to examine other things as well. Now, let's go back over here, and the next thing I want you to think about is outliers. And more specifically, I want you to think about outliers of residuals, but we're also going to examine outliers of x and y too. But again, for right now, what I want to concentrate on is how would we examine to see if we have outliers for the residuals. Well, for the most part, what I would probably want to do is look at a box plot of the residuals. So I wish I'd done that before I left. So if I take a box plot of residual, you can see that I don't have outliers or an outlier. So it seems to be in the simplest case, from the simplest perspective, that we don't have an issue without residual outliers. Now, you probably can tell by the tone of my voice, it's not going to stay that easy. It's going to get a little bit tougher. So, kind of a pretty good way to examine outliers is to look at standardized outliers. I'm sorry, a good way to look at residuals is look at standardized residuals. So a note here, another method for examining I hope I spelled that right, examining extreme outliers is the way I kind of like to look at this. I like to look at the absolute value of the standardized residuals, which we talked about in the last video. If these things are greater than or equal to positive 2, actually for the most part 1.96, I tend to call that at least a mild outlier. Typically, I look at these. If it's a standardized residual is greater than 3, I typically refer to this as an extreme outlier, and I kind of usually refer to these, very kind of subjectively, if you will, as a mild outlier. So guys, outliers must be, residuals must be examined, and if we end up with a subject or item that has an outlier, we would want to examine, what our model looks like with and without that case in our analysis. Now, it just hit me on something. I'm kind of stuttering here because I'm thinking and talking too. Let's not get confused here, okay? Where we're headed from in this video is we're examining more of the effect of cases. Should a case be dropped? So for example, let's say we come down, we have an I plus 1 case, so we've got n subjects that we've created our model from, and we've got k predictors to be consistent with the notation we've used before. We've spent a lot of time talking about extra sum of squares. And guys, extra sum of squares examines whether or not we can drop coefficients for, for example, could we drop certain coefficients? So let's say we built a model on x1, x2, and x3, and we've got 4 variables. Well, should we add x4 in? Well, that's where the extra sum of squares takes place. What we're actually doing in this illustration, not yet, but that's what we're getting, is we're going to be examining cases. For example, this 115th student in our analysis, that person turns out to be an extreme, have an error value that's an extreme outlier. Well, what should we do with that kid? Should we leave the kid in, or take the kid out? So should the kid be left in, or should the kid be left out? So it's kind of in the same ballpark as what we've been doing with the extra sum of squares, but guys, keep in mind it's drastically different. Now, guys, as you can probably imagine, it's going to get a little more difficult, and what we're going to look at, and I think it gets a lot more fun, is we're going to look at more refined measures to examine extreme outliers. Now, it turns out that we have outliers of kind of 3 categories. We have those that are an outlier to the x. We have those that are an outlier to the y's. And we have those that are an outlier to both. Now, if you look at a situation here, again, I'm looking at just the standard scatter plot of x and y, and let's say that we've got some nice manageable data here. An example of an outlier to the x may be if we had that point. So guys, this point right here would be a case, an outlier relative to the x. Notice in terms of the y's, it's within the central focus, but relative to the x's we have in our data, this x is clearly outside the bounds of what the other cluster of scores. We could also have with respect to y, the one we may have there would be something like this. Now, this outlier wouldn't be as much concern for me, because when I come down and take a look at that particular level of x, then I've got some other data points there that can kind of soften the blow of that particular outlier. However, for this x value out here, I don't have anything to soften the blow of its effect. It's going to truncate, it's going to not restrict the variance, it's going to increase the variance in x quite drastically. We also have outliers kind of to x and y, which may be something like this. And that doesn't really concern me as much either, because if you think of the regression on the existing set of data, this point right here really isn't going to change things much. In isolation of points 2 and 3, if I added point 1, my model would change quite a bit. Consider isolation of points 1 and 3, then adding that 2, that second point as an outlier for y would change things quite a bit. So guys, just keep in mind that not all outliers have a strong influence. Our first one, I don't know if you guys can see that or not, but it tells me my Mac cannot connect to iCloud. If not, you didn't see that, you have no earthly idea what I'm talking about. But one of the outliers we looked at was not too influential, because the other cases on the x level, so I'm talking about the number 2, the other cases on the x level would kind of soften the blow. The point number 3 here wouldn't have much effect because it's consistent with the model, even though it is an outlier for x and y. But the point that would probably concern me the most would be this point right here, because I could see where it would have a drastic effect on the slope and the intercept of the model. All right, so guys, hopefully this is making a little bit of sense to you, and we can go on with some bigger, better stuff. Now, I just want to make sure, let me jotted down a couple of notes here. I just want to make sure that we're kind of setting the stage for what's to come. And it looks like we're in pretty good shape here, so if I can get my paper, I'll sit up here. Okay. All right, gang, let's just start thinking about what is a basic solution to error outliers. So first of all, easy to examine. With a simple linear regression case, what do? Well, I would examine a box plot of the residuals, and I would examine a scatter plot of the residuals as y over x or the fitted values. So either one of those in the simple linear regression case is going to work fairly effectively. What happens when we move to the linear regression case? Well, guys, not so fast. We can't sometimes do the simple linear regression stuff when we get into the world of multiple linear regression. What I want you to know is that it's more difficult to identify these kinds of characteristics in the multiple regression than the simple linear regression. at the end of the day, simple linear regression techniques may not help us at all. For example, some univariate outliers in a simple regression may not be an outlier in the multiple regression case. And the converse of that, some multiple regression outliers are detectable in the univariate procedures. So guys, anyway, that's where we're headed here. We're headed with a much more thorough examination of what we do and how we determine outliers that are really kind of giving us problems in the multiple regression world. So guys, before we get going too much, let's just recall that the residual, when you get into big boy, big girl statistics, it's called your error. And it's just the observed y minus the predicted y. And the standardized residual. And again, we usually call that the semi-standardized residual. And to notice the difference, we put a star there. And I hope you remember from the last video that the standardized residual is found by taking the error divided by the mean square error. All right. Now let's go do some stuff. Guys, from many moons ago, you probably recall a matrix that we encountered in matrix operations for the most part, to examine multiple regression models. We came up with a hat matrix. And at the end of the day, the hat matrix comes from the following, that we can find our fitted values by taking our X design matrix times the beta matrix. But a little bit of substitution here shows you that you can replace beta with this matrix. That's the way we saw betas in the multiple linear regression case. And guys, then by just regrouping we can see that we get this new matrix, which we call our hat matrix, which is, at the end of the day, does what? It turns our y's, our observed values, into our predicted values. So at the end of the day, we can simplify this by saying that y hat is equal to our hat matrix times our y's. Now, we furthermore get this up there where you guys can see it. We remember that, of course, our errors are our y minus our y hat. And we have now seen that from this line, that our y's can be expressed as, well, our y hat can be expressed as our hat matrix times y. So it shouldn't be any surprise here that we have I minus h times y as another way of finding our error vector, so our vector of residuals. Now, back a little further, a little bit more review. We should remember that the variance-covariance matrix of our residuals, now guys, this is not to be confused with the variance-covariance matrix of our betas, but our variance-covariance matrix of our residuals can be found by this. Now, what this tells us, from this, it tells us actually a couple things. So let me put 1 and 2. It tells us, first of all, that the variance of a particular error let's just call it E sub I, which is denoted by this mess, can be found by taking this product. Now, this is just the variance of the common variance, and what this is in our hat matrix. The values on the diagonal are the HII that I speak of right there. So we can say that. Let me get up here. HII is the ith element on the diagonal of our hat matrix. Okay? And it turns out those things are really, really easy to find. Well, I don't know about easy to find, but they're kind of easy to find. And we can say that the covariance between error I and error J, where I obviously isn't equal to J. If we have I equal to J, then we have just the variance. Well, we can say that the covariance between E sub I, E sub J is equal to the common variance times the element of the matrix that corresponds to the the ith row in the J column, if you will. And of course, this can be seen as negative Hij sigma squared. Well, guys, again, we should know by now that our estimate of sigma square is the mean square error. So putting this all together in a compact fashion is really going to be helpful to us. We can say that the variance of a particular error, I don't know what I want to put, that the variance of a particular error is going to be equal to the mean square error times 1 minus HII, which again is the diagonal on the hat matrix. And the covariance of any two errors, which at the end of the day, covariance is something that we talked about a little. We haven't spent a lot of time in it. Well, covariance is just kind of a more general way of looking at how two variables vary. Variance is a specific type of covariance. It kind of looks at how a variable varies within itself. And so this is it can be thought of as kind of a correlation, but the correlation uses standardized measures, where covariance uses the measures that the variables are actually measured in. So anyway, guys, we can see from back up here that this is going to be negative Hij times the mean square error. And again, obviously, just make sure there's no misunderstanding there. Let's do that. All right, gang, got a simple data set for you. So let's come in with some x1s and some x2s, and let's come in with a y. And I'll show you what I want to create here. So 14, 19, 11, and 12. Actually 12 and 11 is the way I have it on my paper. And 25, 32, 22, and 15. And our y's are 301, 327, 246, and 187. And what I'd like to do, using R is I'd like to create the following. I'd like to first of all create our predicted values. I'd like to create the errors. I'd like to create the HII for each. And I'd like to create the variances at for each of the errors. Okay, you guys up for the challenge? I may have to actually cut this one a little close or a little short because I'm kind of running up against a let's see, I gotta get my daughter at 4. Okay, let's see what happens. All right, guys, what I'm going to do here is I'm going to just use new x1 so I don't have to shut things down. Guys are probably sitting there screaming at me. Now this is when I need some music. I found a really crazy song the other day that I wanted to play for you guys. My daughters don't agree that the songs are crazy, by the way. All right, so we got some, I haven't masked, no, it's capital Y. So notice up here I use lowercase y, and down here I use uppercase Y to R. That's like Pluto and Venus, two completely different, two different planets. So, guys, as I would hope you would know by now, to create some of this, we're going to have to create some matrices. So the very first matrix that I want to create is going to be my design matrix. And I don't really like that, but oh well, no, I'll have to live with it. So my design matrix, I'll tell you what, I'm going to redo my integers first. So So I need a repeat integer, and I need ones, 3 of those, right? No, I don't. I need 4 of those. So I need my design matrix to be matrix C. I want my ones first. I want my x1 second. I want my x2s next. The number of rows I'm going to have are obviously 4. And the number of columns I'm going to have are obviously 3. By row will be equal to false here because I want these things read, not by row. Okay. Now let's just make sure I've got my design matrix, and it actually turns out I do. Now my response vector is going to be the y's. So I want to put those like this. And in row is going to be equal to 4. In column is equal to 1. And by row is equal to false as well. So let's make sure the response vector is what I need. So gang, I've got everything I need to create my hat matrix, right? Now, guys, if you, again, recall the hat matrix. The hat matrix is my X. Well, I've called that my design. So I'm just going to call the hat matrix H. So I need my design matrix times the inverse of transpose of the design times the design times the transpose of the design matrix. So guys, you can see H, and you can see that the values on the diagonal are equal to 0.387, 0.951, 0.6614, and so on and so forth. Now, what I'd like to do is create a list of diagonals. And let's just call these HII, just to be consistent with what we've done before. And I can come in and actually do diagonals, and I can create a string of the values on the sitting there praying that that was going to work, and it actually did. Now, what I can do now is I can turn my use the hat matrix to create my errors. So my residuals are going to be the so the errors will be let's see what forgetting what I want. I want my predicted values, the y hats, and the errors. Okay, so let's call these y hat. All right, and I will use matrix methods throughout all the calculations here. So remember, the y hat can be found by taking the hat matrix times the response vector. So that's actually what the y hat matrix does, is it turns those into the response values, the y's that were given, into the predicted values. So guys, residuals here, I can take the observed y, which is my response, minus the predicted, which is my y hat, and I can see that my residuals are the following values. Now, the next thing I need to do is I need to create the variance covariance, so I can get the diagonals from that matrix. So it turns out to get the to get the mean square error, which we're going to have to do first. So let's create the mean square error. So the mean square error is going to be the sum of the residuals squared divided by n minus 3. So I just have a degree of freedom here of 1. I have a sample size of 4. I have 3 predictors I'm using, which is beta 0, beta 1, beta 2. So I have 3, so I have 4 minus 3, which gives me 1. I don't know why I divided by 1 because it was kind of irrelevant, right? So our variance covariance matrix of our errors is going to be the mean square error. So let's just go ahead and see what that is, because I'm going to have to. So this is going to be 574.8893 times 1 minus the diagonal. And what did I call that? Did I just, I thought I did, oh, HAI. So this is what I get in this case. So guys, I can create a really cool data set now. Use data frame. So going back to what I wanted before, I wanted my x1, and I wanted my x2, I wanted my y, I wanted my y hat, I wanted my errors, I wanted my HIIs, and I wanted my shoot. Well, I can do this. Let's go 574.8893. I should have saved that as something. Times 1 minus HII. That should work. So guys, now I've got a nice cool data set of some values that help me in determining whether or not a residual is of concern. Okay? Now, I want you to notice something. First of all, notice that, well, let me go back over to what I want to show to you is this. I want to point out a couple of things. Notice that that our predicted value for the first observation so this is going to be the first observation plus beta 2 is going to be the same as I'll tell you what, subscripts really keep me on my toes. Those are going to be the same values. Why? Well, the first one is what? Our predicted value is x times beta, and our second is using our hat matrix. H times y's. So you can see that up here, we've done exactly that. We've taken our betas and multiplied it times our x's. And in this case right here, we've taken the diagonals on the hat matrix times our y values. So kind of cool, I think. So let's go see if we can show that. So the predicted value for the first, so we need our design. Well, first thing we got to do is we got to get our beta matrix, don't we? I haven't even done that yet. So I need to solve T design. We should be really good at this by now. We called it our response, didn't we? So guys, there's our betas. So if I take my design, did I capitalize that? No, I didn't. So our design times our beta. And if we take our hat matrix, what do I call that? H times our response, which is our Y, you'll see that we get exactly the same thing. All right, so I think that's kind of cool. I don't know about you, but I think it's kind of cool. Let's go back over, and what I would like to do next is investigate this my daughters were watching my videos the other night, and they're like, "Daddy, your arms are ugly," or something to that effect. So now every time I see my arm on the screen, I'm going to think about them saying that and be self-conscious of it. Not really. So guys, to estimate our variance covariance matrix of our residuals, now what are we going to get? Well, we're going to get a matrix, obviously, and things on the diagonal are going to tell us one thing, and then things on the upper or lower triangle are going to tell us something different. Just remember the things on the diagonal give us the variance, and the things on the upper triangle or lower triangle, which are going to be symmetric, will give us the covariance. So guys, remember that the variance of our residuals can be found by taking the mean square error times I minus H. So, furthermore, we know that the variance of a particular error is going to be the mean square error times 1 minus HII. So what I ultimately want to do, the question I want to address here is what is the variance of error E sub 1, and I want to say what is the covariance between E1 and say E2. All right, so this is not going to be bad to do at all. Okay, now guys, what we need to do first of all, we need to create the identity matrix, and I'd say more than likely there's a lot easier way to do this than what I'm going to do it, but I'm okay with this one. That may get really ugly if I needed to create a 50 by 50 identity matrix, but you can see obviously what I'm doing there. So in row equal 3, and in column equal 3, and by row equal true. I think you've only got to put T there. So you can see that we have the identity matrix there. All right, cool. Now, next thing I want to do is I want to create I minus H. So I'm just going to call this I minus H, or the IH, I guess. So if I go I minus H, I keep forgetting that's what I call my hat matrix, right? Yeah. Okay, non-conformable. Now, what's going on here? Oh, wait a minute, guys. We have sample size 4, don't we? Oops. My bad. I tell you what, I'm going to use the trick here. Wasn't thinking. So let's call this I2. So my first, I'm going to need 0, and then I'm going to 0, comma 1, 0, 0, 0. So that takes care of row 2. And I need a 0, comma 1, comma 0. And I need 3 zeros and end up with a 1. And I need 4 rows instead of, I got sloppy there. I'll tell you what I did. I was thinking variance covariance matrix for the betas. And I told you guys, 13 seconds ago that that's not what we're doing here. We're doing the variance covariance matrix for the errors. So guys, I got sloppy. Well, shoot. Dadgummit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, guys, what do I need? This is getting old. So I need 1, 0, 0, 0. Okay, this is the one I'm off. Yeah, I think this is going to do it. All right, perfect. Finally. Expedite, quick, no problems. All right. So now let's see if we can pull this off. So I'm going to call this IH. First mistake I've ever made. You got to be kidding me. Oh. You're probably sitting there screaming at me. Darbra, why are you doing that? Because I'm a bozo. All right. So we have this right here. Okay. So guys, the variance for the okay, because I'm losing my okay, I'm kind of losing my I don't know what I accomplished here. Okay, so I need to take the mean square error. This is where I'm going to run into problems. Yeah, let me, so I'm going to have to take 574.8893 times IH. All right, okay, now we finally got it. For some reason, I just thought that the mean square error was supposed to magically disappear and never come back again, but obviously from the notes I tell you it did. So guys, I wanted to address a couple of questions here. First of all, what's the variance of the error E1? And we can see that that's 352.02. And the variance of error 2 is 28. The variance of error 3 is 194, and the variance of E4 is 0.23. I don't know about you, but that's a major red flag, because we need constant error variance. And I don't know, but to me, 0.23 and 352 don't appear to be equal in my book, considering, again, this is sample data and we're generalizing, but I don't think that that we can conclude that the variance for error 1 can be equal to the error of variance 2 considered those two estimates. So, guys, I'm going to conclude here that the residuals do not have constant error variance, but keep in mind data set's extremely small, and I made this up on the no, I didn't actually. I got this. I think I got this from a book. And also what we can see is I said I wanted you to look at the covariance between E1 and E2. Well, the covariance between E1 and E2 would be negative 99.24. The covariance between error 1 and error 3 is negative 261. Guys, to have independence, we need no relationships between the errors. So it looks like that the errors should be independent. And from this, I'm not seeing that they would be, because the covariances appear to be different than 0. So you notice some of them are positive, some are negative, but I'm pretty sure that a larger data set would correct this, but we'll maybe work with a larger data set here coming up. So, guys, don't forget what we're doing here. We are go back over to the so the goal, the focus. Is where you're focusing on outliers for y. And since y is dependent upon x, anytime we examine y, we typically examine the residuals to get that. Now, guys, I will tell you outliers for x. Next video. And I will tell you too, this is it's amazing the hoops that we have to go through to create an online class or to create a graduate class that's taught online. And the great thing about it, the bad thing about it, it's pain in the behind because it takes so long. But the good thing about it is it really makes you think about what you're doing, and in the context of you getting prepared for your master's thesis. Guys, you're going to have situations where you're going to have kids or whoever it may be, you're going to have data, out in the quote-unquote real world that, you're going to have something like this. You're going to have, an IQ and maybe ACT, and you've got these ACTs that are, pretty close, and then all of a sudden you've got an ACT of 63. Well, common sense kicks in and tells you that ACT at most can be 36. So whoever was coding the data must have transposed that, and it should be a 36, possibly. Or maybe they just hit the wrong key and it's supposed to be a 23. Who knows? But if I give you a variable up here, just a random, not random statistically, but kind of just some variable in your data set, and you don't know the context of the measurements. For example, let's say the 63 is something that could be attained, where it couldn't be in the ACT. Well, you're sitting there looking at that, and that's clearly an outlier. And of course, it'd be more appropriate if I told you now that we're looking at the Y's, but that's clearly an outlier, right? And you're sitting there trying to think, is that an outlier just from the fact that it's just a different measurement? This kid scored incredibly high or incredibly low, whatever we're taking a look at. Or did the person transpose the numbers? Is this a typo? So you're sitting there and you're trying to think, what in the heck's going on? But at the end of the day, what you've got to ask is, does this value inappropriately influence the results of my analysis? And I'll put analyses because we typically have multiple things going on and things as complex as a master's thesis. So, guys, I tell you what, I need to stop this video. I really am ready to go on because it's actually going to get pretty cool. But I'll do the rest of that. I don't know, maybe later tonight or I don't know, tomorrow, whatever it may be. And we'll get into more of this stuff in the next video. So, guys, I don't want to end, but I got to. My daughter needs to go to gymnastics.